Welcome to another lesson on infinite series. This time we're going to focus on power series, which is where we introduce variables into the idea of geometric series. So what you see on your screen here is a collection of partial sums that are trying to approximate this function over here, and that's in black, 1 over 1 minus x. So let's jump right in and understand why and what is happening. So first of all, the why is this series equal to this function over here? Well, this series looks familiar, and so does this function, or what I'd call it as a sum. So I'm going to tell you a little bit about this, that if this is a geometric series, that means the first term is 1, and that means r is equal to x. Remember, this is in the form of a over 1 minus r. So that means the terms are 1 plus x squared, and so on. And really, that first term right there is x to the 0. What I want you to do is leave a little space in your notes to define a power series, but right now let's just create some partial sums. So we kind of need your calculator here, and I'm just going to go y1, 2, 3, and 4. And these are basically the partial sums, sum 1, sum 2, sum 3, and sum 4. What I'd like you to do right now is enter, well, after this, pause the video and enter 1 as your y1, 1 plus x as y2, and so on. And then I'd like you to enter this function, 1 over 1 minus x, as y5. So pause the video, do that, and come back. So what I did was I took that information and I entered it in. I did a zoom decimal, and it gave me this visual here, which was the beginning of our video lesson. So I want to point out what I did was I worked with the colors here, so I made the function black, so that's 1 over 1 minus x. And then the first partial sum is just this red line. So you should have a horizontal line as well. And then the next one is the orange line. So I did a Roy G. Biv sort of thing without the yellow. And then the next one is red, orange, yellow, blue. Okay, the blue is the cubic function. Oh, sorry, the squared function, the green, red, orange, yellow, green. That's the quadratic, and then a cubic. I understand that this doesn't mean too much to you right now, and it's pretty difficult to see, but I'd like you to try to focus with me here. I want you to see that there's this space where the quadratic and the cubic function, kind of in this space between 0 and actually a little bit further left, there's this point where they're kind of coming together. All of the curves are together, and they're together all the way up, not quite to 1, but in this window around the origin. So there's this basically what we'd call a center of approximation, that if we were approximating 1 over 1 minus x at x equals 0, all of these curves or functions do that well. But the more we move away from the origin to the right and to the left, the less they approximate that function. But really all I want you to see is that between -1 and +1, that these functions are trying to approximate that function. Sorry, the series, the partial sums are trying to approximate that function. And the more and more partial sums that we use, the better it's going to approximate that function on that window. So that's all we're trying to see right now, and we'll talk about what that actually means in just a moment. When I look back at this question, why is this true? The answer really is that if we're allowing this sum to go up to infinity, really this approximation in this window is going to be really, really good. In fact, it might even extend beyond that. So that's all we're talking about right now, is that curve becomes the same function, or the series becomes like the function. All right, let's define what a power series is before getting too confused. So here we go. This is kind of our basis here. This is an infinite series, a sum that's represented by a polynomial, which is really more than just a polynomial. It's really an infinite number of terms type of polynomial. An infinite nomial anyways. This is centered at x equals 0. If it wasn't centered at x equals 0, there would be this x minus a value, like x minus 1 or x minus 5 or x plus 2, a transformation. But like I said, this piece right here is a sum, and then this piece right here is a polynomial. So in essence, one of the things that we're studying right now is how we can represent a polynomial using a sum. Or in other words, is it possible that we could add a bunch of terms together and we create a function? All right, so I'd like you to turn the page and check out this exploration. I want to send you loose a little bit on your own to see if you could make some connections here. And don't worry, I'll have some of the answers for you for the first few so you could use them as samples. But read along with me. Given that 1 over 1 minus x is represented by the power series 1 plus x squared plus x cubed all the way up to x to the n and all the way up to an infinite number of terms on the interval -1 to 1. Now, a side note, remember this -1 to 1 is meaningful to us because this power series is actually a geometric series such that it converges on the interval -1 to 1, as long as that r value is less than 1, right? Okay, so still a little bit of confusion between what's the difference between a power series and a geometric series. So for the first one, what you're trying to do is you're trying to find a power series that represents this function. So we're coming up with the terms first and then coming up with the general Riemann sum. So let's do the first one together and see if you could do the next one. What I'm noticing here is that this is in the form of that sum of a geometric series. So the first term is 1, and then this is the r value right here. Or is it? Wait a second. It doesn't have the right sign. So this is actually 1 over 1 minus -x. Okay, so it has to be in that form 1 over 1 minus. All right, now I could write this with the proper information. So 1 is the first term. We multiply the first term by -x, so the next term is -x to the 1. And then we multiply that term by -x, so that's -x squared. All right, and then we could go on forever. And then we're going to try to write a general term, like a Riemann sum for that. So see if you could write the Riemann sum, and then I'll have the answer here for you in a moment. And then you can move on to the next one. So there's your start. All right, so hopefully you tried that and you realized that since the a value is 1 and the r value is -x, we have this Riemann sum. Okay, now your next challenge is to write number 2 similarly to this number 1, kind of adjusting things, and then notice that the first term changes. So pause now, try that out. Okay, this time we have a similar setup. So this is x over 1 minus -x. So we have terms that look like this. X times -x and x times -x squared. And so on. So see if you could write the Riemann sum for that. Pause and come back. Here it is. We have to get too crazy with what this actually is. I could just write it like this. Or you could get fancy and do -1 to the x, to the n, times x to the n plus 1. So either of those work. Oops, that's a little or. Great, okay, so try number 3 and 4, then I'll come back and I'll have the full solution, well, most of the full solution for you. Alrighty, I hope you tried those out. Otherwise, not much use to this here. We're getting familiar with writing out the terms of a sum. Like these are representing functions, these are representing the actual series written out, and then the Riemann sum, which is the general term, the sum of the general term. So don't be confused in how, like, wait, why should I have to write all three of these things? What's the difference? It's knowing that this, in purple, these functions are represented by a sum of terms, and that sum of terms could be written succinctly with the Riemann sum. Alrighty, well, I have two examples for you. One involves differentiation and one involves integration, but that'll be in a different video. What we could do between now and then is take a look at number 5 and 6, work those out. Just a little tip for number 6, that 1/3 that shows up in front of the parentheses could be used as your a value, the first term. And then you should be able to find the terms of the series, the Riemann sum of the general term, as well as the interval of convergence. It's basically transformed a little bit. All right, thanks for watching.